Hello everyone. Thanks for the kind introduction and the opportunity to speak here in front of all of you. Yes, as I already was introduced, my name is Wiebke Reichstein. I am the lead at Univercell. Univercell is a German-based company. We are located in the northern part of Germany, next to Kiel. And our main focus is normally lithium-ion battery technology, where we are producing customized electrodes as well as cells. Nevertheless, we are also very interested in new technologies. And one of them is sodium-ion batteries. And therefore, I'd like to give you a short introduction into sodium-ion batteries in the next couple of minutes. And hopefully in the end, I can convince you that sodium-ion batteries are wise to consider, and also a possibility for new just to replace some lithium-ion batteries at certain applications. Let's start with some numbers. So as we already heard today, the market for lithium-ion batteries especially is growing really rapidly over the last years and will also grow in the next few years. So at the end of 2030, we have roughly a factor of 6 in the growing field. And this is here divided in several sectors, and the main driving motor here is the mobility sector, with the EV sector at all. But nevertheless, also the stationary storage systems will also grow really rapidly in the next years. And here's a common sense that the sodium-ion batteries will take place or are the main applicational field for sodium-ion batteries. So if the demand is going up and up and up in the near future, what about the costs? The costs will go down or already went down. So here's a study where several different studies were taken together, and in principle the prediction was, and still is, that prices will go down. And this is mainly the reason because we have former prototyping, and now we are going to the mass production. So we have just the economic in scale. And also for lithium-ion batteries, we have, for example, new chemistry evolved. For example, the nickel-rich materials, which also give us the possibility to lower the thickness of our materials because of higher specific capacities, and therefore we can also produce a little bit faster. Nevertheless, we also offer, for sure, better yields because we produce more and more. And now the question comes, okay, where are the main cost drivers here? So why have we still this kind of higher prices, let's say it? So for this, we could also have a look at the manufacturing costs as well as the energy consumption costs. And here we clearly see that due to the state-of-the-art mixing process at the moment, this is still the wet process. And therefore, we use solvents. And the solvents are just mixed with all the active materials, but after the coating, we have to dry everything out. That's why we have a really huge amount of energy consumption in this field of the drying process. And if you compare now sodium-ion batteries with lithium-ion batteries, you see that the manufacturing steps are almost the same. So the good thing is, for lithium-ion batteries, for example, you have a similar technology of sodium-ion batteries. And that's why we have, we could use the same machineries we are currently using also for the lithium-ion batteries. But on the other hand, we will not see a real cost reduction if we go now from lithium-ion batteries towards sodium-ion batteries. And now's the question, where is there some kind of benefit if we go to sodium-ion batteries when we don't see it here in the manufacturing costs? Well, therefore, we have to consider the material costs. Here's a chart where we or where I just have 3 different cell types, so 2 times lithium, NMC and LFP, and in black, sodium-ion batteries. And now it's just subdivided in all the different components you're using for sodium or for cells at all. And now if you have a look at the cathode active material, you clearly see a clear tendency that the sodium-ion battery have a clear cost reduction here. The NMC is way more expensive compared to sodium-ion batteries. Another point I want to point out here is the current collector for the anode. As you might always know that in lithium-ion batteries, we are using copper as a current collector. But for sodium batteries, we can also use aluminum, which will also reduce the cost even further. The active material on the anode side is a little bit more expensive at the moment for sodium-ion batteries. But this might be also in the near future also reduced a little bit, because we have here the possibility to use also biomasses as synthesis raw material here. So bringing all the points together and summing up all the costs, you see that sodium-ion batteries has the really pro on the price here. It's more or less comparable to LFP, but NMC still is way up in the price. Another main concern we also have to consider if we are speaking about lithium-ion batteries is, how much lithium is on the Earth. Well, comparing now sodium and lithium, you see that sodium is 42 times more common in the Earth crust compared to lithium. And this is why you can, for example, mine sodium in principle all over the world. So you can use rock salts, for example, seawater, just to get the raw element. For lithium, this is different, because there are just certain countries where you can mine lithium. And this will also lead to some geopolitical dependencies, which might be an issue also in the future. And bringing now everything together brings up that sodium is just 1/100 in the price compared to lithium. So now let's have a look at the figure of merit for sodium-ion batteries compared to lithium-ion batteries. And let's focus at the moment just on the energy density. Well, you see, for lithium-ion batteries, you have a kind of a huge range. This is mainly caused by the fact that we have different cathode materials. So LFP on the lower end, and NMC on the upper end. And if you have now a look at the sodium-ion batteries, well, it's a little bit lower compared to lithium-ion batteries. So it might be, or is just the case, that we can compare sodium-ion batteries more with LFP cells. So sodium-ion batteries will be more a replacement for LFP cells, but not so much for NMC cells. The price is also kind of different, but I already talked about this some slides before, so just the sodium ions has here the big advantage in the price. The cycle life is also kind of different for those two types. The lithium-ion batteries have here a clear pro here on their side, so they have higher cyclabilities compared to sodium-ion batteries. This might be caused just due to the size differences in the ions. So if you have a bigger ion, which is sodium in this case, this could also induce more stresses or higher stresses in your substrate material if you intercalate the ions in and get them out at the end. So this might damage the material sooner. But maybe in the future, if we do more development work and have new materials, well, these numbers could also go up in the future. So where could we use now sodium-ion batteries? Well, as I mentioned in the beginning, the energy storage application is one really huge field where we can use those sodium-ion batteries, because they have lower energy densities, well, that doesn't matter so much if you just have your battery pack there and it's just stationary. Another point is, for example, the logistics sector. For example, for forklifts. In the former times, they used lead-acid batteries. Right now, they are using lithium-ion batteries, but as a counterweight, they're putting also lead in the free space. And now, you could just replace lithium-ion batteries by sodium-ion batteries and also reduce the lead because you just have heavier cells, for example. The telecommunication sector is also one possibility where you have radio towers, where you need emergency power supplies, where you could also use the sodium-ion batteries. A niche application might be the submarines, so in the defenses applications. Let's have a look at the anode material. So in lithium-ion batteries, you normally use graphite, but this is not possible for sodium-ion batteries, just due to the size difference in ions. And anode for sodium-ion batteries, well, you have different possibilities, but hard carbon is mainly the way to go, I would say. How does hard carbon look like? It's a disordered carbon structure. And you can also synthesize this. For example, here in this paper, it was studied from olive stones. Well, you can use biomasses, for example. So how does the intercalation of sodium ions work now? Well, they have two different areas, but still there's a kind of debate going on in the literature. So it's still in discussion and also ongoing research here. One suggestion was given by Stevens and Ahn, where they just claimed, okay, in the sloping area, we have more the intercalation of sodium ions at defect sites. And in the flat region, we have more an adsorption of the sodium ions and filling micropores, so the sodium ions go between those carbon layers. On the cathode side, well, there's a huge field of ongoing research at the moment, and there are different kinds of subgroups. And they all have pros and cons. I just want to focus on a few, which is, in our opinion, more reasonable also later on in the mass production. And those two groups are, one is the layered oxide groups. So because layered oxides are already known in lithium-ion batteries, and they're well investigated. And we know that they are working kind of well. So hopefully they will also work really nicely when we're using them for sodium-ion batteries. Another field is the Prussian blue, and this is really nice because it's kind of a cheap material. However, it's kind of moisture sensitive, so it always comes with a pro and a con. Okay, so to conclude my talk, at the first, I hope I could convince you that sodium-ion batteries are wise to consider and might be a good candidate, for example, for some applications to replace lithium-ion, especially LFP cells. The main application will be the stationary storage because of the lower density lower energy density compared to lithium-ion batteries. The big pro for sodium-ion batteries is just that we have a more sustainable material here. We have less expensive prices from materials because sodium is much more common compared to lithium. We don't have the geopolitical dependencies, but nevertheless, we still have a lot of developmental work to be done until we reach really the point where we are at the moment with lithium-ion batteries. And with this, I'd like to thank you for your attention, and I'm happy to answer any questions.
Thank you very much, Wiebke, for this comprehensive comparison between lithium-ion and sodium-ion batteries. And actually, there are further questions on this. And So, first of all, do you see a further scaling effect in cost for the sodium-ion batteries, or is it already included in your comparisons with regard to the cost calculations you made?
Well, for sure, all the materials which are right now on the market, I think also even for hard carbons, they are a little bit more in the price, so they are more expensive at the moment, and because lesser companies are just selling this material.
Yep.
So I think in the near future, this prices could also go up, or not go up, but go down.
Okay, so it's not included in the calculation yet, but you see will be further advantageous for the sodium ion in the future. Will SiB be recyclable?
I guess so. So I don't have...
Question would be why not?
I don't have any kind of studies in my head right now, but I guess so, because we also could recycle lithium-ion batteries, so I think, but there's still also a lot of research to be done.
Okay, further questions. Another dimension here is being asked for, the weight. Can you compare the weight of SiB batteries against LiB? How does this affect the application range?
Yeah, well, I just compared the energy densities. So in principle, this is also associated with the weight in the end. That just the sodium-ion batteries will be more heavier compared to the lithium-ion batteries, just because we have a lower energy density. That's why we just have to coat, for example, thicker or put more cells in one package to get at the end the same energy out of this. So, and in principle, how affects this the applications? Well, I already pointed it out that we have more the focus on the stationary applications or energy storage, and not in the automotive sector, for example, where weight is really crucial, for example.
Okay, good. Clear answer. Are there any safety concerns regard to batteries? How about thermal runaway?
Yeah, so safety concerns, well, sodium is kind of reactive a material or element, as well as lithium. Nevertheless, there are still some issues going on, or we have to see, for example, if we want to replace, for example, LFP cells, and LFP is really known for its safe and lower price. So we definitely have to look at this field as well, that sodium-ion batteries, if they want to or should replace LFP, for example, we definitely have to consider also the safety issues, because there are some points definitely to consider.
How to consider? Any recommendations, basically?
How to consider? Well, you just have to...
Packaging or something like that? Packaging or safety regulations needed?
Yeah, you just have to, for example, some electrolytes are just, you just have to adapt them in the correct way, that they, for example, don't attack your anode or cathode materials. So this would be, the worst case, I would say.
Okay. So sodium sounds quite attractive over LiB, but still requires highly toxic materials as well to stabilize. For example, cyanide, vanadium. Will this limit the sodium battery uptake from your point of view?
Well, good question. But I think, in principle, we always have to use some kind of toxic materials. But I don't know how to answer this question now in detail.
No clear-cut answer possible, because
it's possible that it's
trade-offs are to be made. Possibly, it's difficult to calculate in the end the net effect or so. That's a bit takeaway at the moment. And maybe we have time for one more or so. Which SiB cathode for which application?
So which cathode material we should use for which kind of application? So, I think it also depends on your prices and your cycle life in the end you want to achieve, because I think every cathode material has also differences in their cyclability, or higher C rates, for example, then you always have to choose from different cathode materials, as you already do, for example, also for the lithium-ion batteries.